Okay, so next thing is need to talk about numbers and science because we just got done with stoichiometry and also when we get into labs, I know, and what you would like to do is you're going to be making measurements um, and so the measurements you can make are in numerical form, and so need to discuss. Okay, like I said, where do we use numbers? We use numbers at stoichiometry that we just covered, and if you're in 121, we'll cover a lot more stoichiometry, and so we have to make sure we know how to deal with numbers. And when specifically in the lab, and during the times when we can't be in the lab doing labs, you still got to be able to know how to use numbers. Okay, understanding numbers in science. Okay, a number in science is different than a number in math. Now that sounds weird, and it seems like a number is a number, but it's actually not. In math, numbers tend to tell us just how big something is. Okay, and the sort of like 5 and 3. You know that 5 is bigger than 3 by 2. Okay, it's just some sort of relationship between something, some abstract thing, 5 and 3. Okay, um, in science, we also have numbers relate how big something is, but our numbers also have to tell us how good our number is. Okay, because not all numbers are created equal. Some numbers are better than other numbers. And what I mean, and I don't mean that 5 is a better number than 7. Okay, what I mean is that when we make a measurement, some of the numbers that we measure are actually better than others, and we're going to be talking about how we can determine that. And so what we do is that betterness or whatever I call it trueness is that what we're looking for in a number. Uh, so how true is the number? This how good is it telling me my what I need to know? All right, because when we look at things, there's always a degree of, of focus that we can't quite get right. Okay, so no matter how good your vision is, it's always going to be blurry. Okay, uh, and so our numbers are the same way. When we make a measurement, there's always blurriness in our numbers, and it's not the so so what we want to do is we want to have the numbers that we write have some way of representing the blurriness of our measurement by looking at a number. So that's kind of, I mean, it's kind of a thing is that what we're going to do is we're going to look at a number and go, oh, I can tell how blurry my measurement is, okay? And so that's what we're going to be looking at. So there's some numbers that are really clear, like, and you can see it really get a lot of information out of it. And some are really blurry, and you can't get very much information. And that's one of the key things here is that we're looking at numbers to give us information. All right. If you have a number that is really true, that has a lot that you can go, oh, I can see that number. It tells me something really good about what I saw. Then, uh, then that gives you a lot of information. But if you have a number that says, oh, your measurement is really blurry, then you go, well, I can't tell you too much about what's going on here. It's like, if you're watching TV and all of a sudden, all it starts going, you can see a body and you can see another body and that's all you see, and you see them waving each other's and they go all wiggly. But the only thing you see is there's two bodies, okay? And then finally your TV comes into focus. Your FPS is quite good, and then so all of a sudden you see intricate individual people, but you start to notice is that there's other things that are blurry, and so that's what we want to do. So our numbers are going to be looking at not how big our or small our substance is, or whatever, not just substance, but our quantity that we're looking at. But how blurry is it? Okay, or or the opposite, how clear is it? Okay, for example, let's say we have a book and we want to find its mass. We need a scale to do this. Well, we're going to weigh it on two different scales. So I have scale A and scale B. And I put the book on both ones. And this scale here comes up 1.1 grams, and this one comes up 1.1023 grams. So the book weighs around 1.1 grams. Yeah, that's a very, very, very tiny book. But so doesn't matter. So it's both of them are kind of give you information about 1.1. Okay, but the numbers are not exactly the same. B has more numbers than A. All right. Now, why? So why is that? All right. My guess, a lot of you would say because it's a better scale. And I would ask you why, and you would say because it has more numbers. Now, I could argue with you and try to suggest that having more numbers could mean all kinds of different things. It could just be, this thing could just be giving fake numbers. I say, I have the scale said, give me numbers, give me 80 numbers. The first two numbers, the other ones that count. All the other 78 numbers are just random numbers. Okay, but that's not the case. We're going to just assume that yes, scale B is scale A, better than scale A. And so, what does better mean? What is it about more numbers that make it better? Okay, scale B, in essence, can dig deeper into the weight and give us more information. So what it does is that what it's doing is this. I mean, you have a hole, and it's telling me I always got this much information. It digs deeper. It says, hey, I got this much more information. So every time it throws out a pile of numbers, those numbers tell us something better about the information. So scale B digs deeper in the weight and gives us more information. And this is why it's better, because it gives us more information. All right, that is, of course, the information true. Like I just was saying, as I could just have it randomly make up numbers. And we're going to just assume this. Both A and B give us true information, but B gives us more information. Okay, more of that true information. Both of them are true, but B gives me more of it. In science, we have a word for this trueness, or how good our data is, and it's called precision. Okay, and precision is a really, really important thing in science, and it just doesn't get enough. I mean, we just don't talk about it enough. Precision is a measure of how good or true a data is. Okay, in the world in the world scales, the more information, the more data, the more precise the scale. No, precision has a couple other definitions. One of the definitions of precision is lack of error. So that means there's a lack of blurriness. Okay. So the more you could either say, "Oh, I have really a lot of data," but actually, what you say, all data is not good, but some data is better than other because it's less blurry. So actually, it's better to talk about precision in terms of error, because what we say is, it's like, you're if you're going to talk about the day, you have a day with less clouds or a lot of clouds, but there's always clouds in the sky, even if you can't see them. And So precision is a lack of clouds, a lack of air, lack of blurriness, and what that means is that you're going to get more information. So you can see that numbers and scale don't only tell you how big a number is, its magnitude, but it also tells you how precise or how unblurry your number is. In math, this quality right here is non-existent for the most part, unless they're using science, explaining, uh, uh, talk about numbers in science. Okay, like if you go into if you do physics or physics problems or whatever, you're always going to have to worry about this thing. But if you're just doing 2 times 7, you're going to get 14. You don't care about this number at all. Okay. Now we would like to compare. Now what I would like to do is compare the precision of the two scales. And what I mean by that is I would like to score the two systems. There's A and B. And is there a way that I could actually give a score to scale A in terms of precision and score B? And that's what we want to come up with. And what we want to do what we want to do is we want to have, like I told you, is we want to have our number give us that. So I typically ask my class to come up with a scoring system. For instance, I had a student last year give scale B. The only thing I said was I want you to give scale B a higher number than scale A. And that's the only thing I said, okay? And the students, and they go, well, I don't know. And I had that year, I had a student come up with, said, well, I'll give scale B a 10 and scale A is 6. And I asked them why they chose these. And basically it said, well, it's, scale B and A kind of give the same answer, 1.1, but scale B is a little bit better than A, so I don't know. So I said 10's a little bit higher than 6, but not by a lot. I go, okay, that makes sense. Then I ask another student to do the same thing, and they might go, okay, well, I'd say, how about 100? I'll give scale B a score of 1,000. I'll give scale A a score of 953. I go, okay, well, that satisfies that scale B has a higher score than scale A, and you give some kind of reasoning why that is. Right. No, the problem is that both of those examples are just sort of arbitrary scales, and they don't really. It's not consistent. I mean, both of them give you an idea, but you like to just have. They will look at it, two scales, and go, oh, this one gets this number, and this one gets this number. I mean, this score. Okay. Without trying to guess, well, it's this one is 10 and this one's 5.3. Okay, so what we want to do is come up with a repeatable method of scoring our precision that always gives a better scale to the highest score, but kind of relates the two scales to each other. All right, I mean, you could just say scale A gets scale B gets score 1 and scale B gets score 0. And B is better than A, but you would like to have it be able to say, well, how much better? Okay, so we want to add that to the score as well. All right. Well, actually, it's really quite simple, this scoring system. Um, the scale A is given a score of 2. And scale B is given a score of 5. That's it. So it satisfies both of what I just told you. Scale B is bigger, I guess score 5, and then A. And it kind of tells you that the relation is that it's somewhat bigger, but I mean it's bigger, but it has some biggerness than B than A, and is a real difference. Okay, so how did I get these two numbers? It's real simple. Notice that scale A has two numbers, 1.1. And scale B has five numbers, 1.1023. All right, we said that the scale with more numbers is better, right? So the numbers of numbers actually is the score. Okay, pretty cool. And so you don't have to come up with some arbitrary numbers to come up with the scoring. So actually, in the numbers, when you write them down, not only tells you how big they are, five is bigger than whatever, 7 is bigger than 2, but also how good your data is. Okay, and some scales will have the right some same precision. So precision scoring, this thing I call precision scoring, is actually given another name in science. All right, it's called significant digits, or significant figures, or sig figs. Now, when you take, I don't know, when I was taking chemistry, it took me a long time to understand and figure out what they were talking about when they talked about this. It just seemed to be this abstract thing, and I wasn't really clear. And so if you have had sig figs before, and you probably have some preconceived ways of doing it, and maybe your teacher taught it right. Maybe they did. Maybe they taught it in the terms of this. But most teachers just talk about telling, when they just plaster a number in front of you and say, how many sig figs does it have? And you don't understand what that means. So when and it's just not any number. So one of the problems I remember doing this stuff is a teacher would say, put up a number on the board, say 3.75, how many sig figs? Okay, well, he's assuming some things, or she. First of all, it's a measurement. Okay, and that there's a scale being involved, and then that scale measures to the hundreds. Okay, so there's all kinds of things that assume that. So when a teacher would put a number up board and say, what's a sig figs? All you do is you see a number, but you forget that it came from a measuring device. And in further analysis, if you take 121, we'll talk more about this in terms of sig figs or precision scores, because they get complicated. Yeah, it's just not, you just can't look at a number and go, what is the precision score? Because you have to be aware of the context that's being involved, which is the scale. And for right now, what we're going to do is we're going to try to make our precision scoring relatively simple. And if you take 121, we'll expand on it. But for right now, just try to get the concept. Okay, so there's another real important thing about your measurement and the number that you write down, or you see on your scale. And when you look at a number on your scale, like 3.75, in math you would say there's a 3 and there's a 0.75. And what you would say is each one of those numbers has equal clarity. Okay, is that there's a 3, there's a 7, and there's a 5, and you're absolutely sure that each one of those numbers is exactly a 3, a 7, and a 5. Okay. In science, because we always have blurriness when we do measurements, is that the numbers are not created equal. There's always at least one number that's foggy or unclear or blurry that you're not sure about, and that's actually a good thing. Um, is that you never can be you'll there's two things. You're always going to be sure about something when you make a measurement. The other thing is, yeah, I mean, sometimes your sureness is that you don't know anything at all. All right. But other times, you at least got some information and go, oh, I see something that kind of looks like a blob, right? I know you'll say, that's a blob, all right? And then everything else, it goes a blur. And then you might have a microscope, you go, oh, or a telescope, oh, a tree, okay? All right, so what we want to do is in our numbers, when we write in our measurement, the measurement that we see, there will always be one digit that's blurry automatically. So you have 3.75. One of those numbers is blurry. Okay, so what do we do? So there's one number that's going to be allowed to fluctuate, and it's our blurry number. It's going to set up the background, all right? And what it's going to do is, so when you look out at, see a blob, you'll see blurriness. So the blurriness actually makes you see the rest of what you really want to see. So, I mean, if everything was blurry, you couldn't see what you want to see. But the fact that you have blurriness and then something that's unblurry makes the unblurry thing or clear thing clear. So you have to have blurriness or fogginess to actually see things. Okay, so all right. So what we're gonna do is we're gonna look at our numbers and which number is going to be our foggy number and which are going to be our true numbers. So an example above, we had 1.1 grams. What we're going to do is the last digit is going to be our blurry number. So the 0.1, which we're going to call the guess digit, is not totally trustworthy. We're going to say it's kind of close to 0.1. Okay. I can't resolve it. I mean, it could be 0.1, it could be 0.2, but I'm gonna say it's close to 0.1. So you're trying to focus in to hitting the point, but absolutely true that the 1 is solid. Okay. So the 0.1, the blurry number, tells us for sure that this number is true. Okay, so the last digit of every measurement is going to be our blurry number, but one thing it's going to do, it's going to make all the numbers before it, it's going to make them true and acceptable. So on the other scale, we had 1.1023. So this number right here is our blurry number. But what that does, it makes these guys solid. Okay. So this is a real important thing in measuring. You're always allowed to have one guess digit, and you're always going to be unsure about it, and that's okay. Okay, if I just wrote down 1.102 as my answer, then that would make this blurry, and these guys good. All right. So there's a difference between these two numbers here. See? All right, well, now one of the biggest problems with our scoring systems and significant figures, sig figs, significant digits and stuff like that is zeros. And that's because zeros, zeros, what does it mean? For a lot of people, zero just means nothing. And so nothing is nothing, and so you don't write it down. Okay, well, uh, if I said 101, 101, well, that zero means something. Okay, it's a real number. It tells me that here's you have 100 and then you have one. All right. So so in science, zeros are a big deal, and a lot of times because in math zeros aren't a big deal. Uh, a lot of times we just throw out zeros, and they're the lost child, they're forgotten child, and so you have to be careful with zeros. Your calculators think zeros are worthless. So if you put in 1.0000 into your calculator and then multiply it by 2, the answer that calculator would come up with is 2. And then you go, where did all the zeros go? And your calculator said, well, I don't need them because they're not there and they're not real. Okay? So, but in science, you would say, yes, those zeros are there. I measured them. So, and you would write then down 2.000. And so we got to get into that. Okay, so a lot of times students, if they see 1.10, what they'll do is they'll just forget about the 0 and write down 1.1. And like I told you, there's a big difference between these two numbers. And let's look in terms of their precisions, okay? So this score, 1.10, has a score of 3. 1, 2, 3. And this number here has a score of 2. Okay, so what you're doing is so if you knock this number out here, you're reducing the quality of this measurement. Okay. So we have to be careful about zeros. Don't ignore them. All right. Now there's times we will ignore them, but we're really gonna try not to. All right. Now let's think about it. Let's say that you measure some value of 10, but you ignore 0. All right. So you leave the 0 out. Well, then what do? You're left with 1. And 1 certainly isn't 10. Okay. So there's a difference between 1 and 10. And 0, it makes a difference. All right. And what it does, it tells you that your number is not 9 or not 11. So my general rule for you guys right now is write down all the digits that you are allowed to write down, and even if they're zeros. Okay. Now there'll be times when you won't do that 0, but for us, we're going to write down zeros. Don't forget that. Please don't forget that. Okay, now let's talk about the actual measuring devices. There are basically two types of measuring devices. There's analogs and digital. And so we're going to look at both cases. So digital are really easy. And that'd be like the scales that we just had. The 1.1 and 1.023. Where you put something you're going to weigh, and it pops up and gives you a number. Now, one of the things you got to do, and this is really simple, is that when you have a digital scale, you write down all the numbers you see. There's no guessing, all right? At least for you, all right? So if you see 1.1020, you write down 1.1020, okay? That last 0, I want to talk about again in a minute, is that you don't forget it. And there's no guessing, I said, but actually there is guessing because the scale is guessing, because what it's doing is resolving this value that's being measured, but it can't get that last number exactly right. So the last digit of that scale, so if you have 1.1023, what the scale is telling you, I think this is 3, but I'm not sure. It could be 4 or it could be 2, but kind of looks like 3. So I'm going to put a 3 here. Okay. But what that does, it makes these guys absolutely clear. All right. Okay. Now, actually, when you do put numbers on scales, sometimes you'll notice is that the last digit will fluctuate. It'll go 3. This number here, it'll go 2, 3, 4, 3, 5, 7, and then bounce back, and then you can sit there forever, but you kind of really don't have to do that. You just go, well, I think it's a 3, and that's absolutely okay to say I think it's 3 because that's in fact what the scale's doing. But if you wait long enough, the scale's going to end up saying, well, it's a 3, but the scale doesn't know. So that's the kind of thing is the scale is not perfect. It's always this last digit is always going to be like, I give up. I can tell you it's 1.102, and I think it's 3, but it could be a 4 or it could be a 2. The last digit is always a guess digit. Always. Absolutely always. Whenever you see the most, precise measurement in the universe, right now, analog measuring devices are one that you have to make the determination of the numbers that it gives you, right? And usually these are graduated scales like rulers, thermometers, and so forth, where it's kind of split up. It's like this. It's like a scale. Here's 8, and here's 7, and it's split into like this. And these are graduates. So you graduate from 7.1, 7.2, 7. So you're graduating up is step. So graduate means step. Then so you're stepping up, okay, and so we're using these step up scales, where we're going to be looking at how we do that. And it's going to be a little bit hard to do this because we have to come up with the numbers ourselves. The scale is not going to give us our value. So let's look at the following measurement, and let's say it's measured volume, and hopefully you'll go over units. I'll go over units of measurements of what we're going to measure in increments of milliliters and mLs. And what we're doing is we're looking at maybe like a graduated cylinder, and you're going from 7 mils up to 8 mils, and it's split into tenths. So this is 7.0, 7.1, 7.2, 7.3, 7.4, 7.5, 6, 7, 8, 9, and 8.0. If you heard me, I didn't say 8. So I said 7.0, I didn't say 7, 7.1. And that's important here because this is 7.0, this is 7.1. Okay? And we'll talk about that in a minute. So let's say I have this measurement right here, and I want to write down what is its measurements. Okay, so I'm going to write down what I got. So it's 7.1, 2, 3, 4, 5, 6, 7, 8. So I know it's 7.8. So I'm going to write that down. And I'm really sure about that. So I know it's 7.8. Okay? Now what I would like to do is that 0.8 I'm really sure about, so what I have to do is add another number to make that number solid. And so I add a guess digit. So I'm going to add another number somewhere between 7.8 and 7.9. That's going to make that solid. And it really doesn't matter what number I pick. It's kind of close to 7.85, but I can see it's made a little bit less than that. So I'm going to write 7.83. Okay? So what that does, it tells me I'm really sure about the 7.8, but I'm not really sure about the 0.3. this 3 right here, which is fine. It's absolutely fine. And like I said, I could have made this a 4 or 5, even a 7. It really doesn't matter. It's a guess digit, okay? But because these two numbers are what's important. Okay, here's another example. Same scale. So here's my measurement right here. I want to come up with it. So it's 7.1, 7, 2, 3, 4, 5, 6, 7. So it's 7.7. Sure about that. Now, if you notice, it lies right solid, right on the 7. Okay, now a lot of students would just go, it's 7.7. Okay, now if you write down 7.7, what number are you sure about? You're only sure about 7, all right? And you're guessing on this digit. What you're saying is that, well, this could be a 3, it could be any of these numbers in between here. Okay, so what we're going to do is you got to add another digit over here. That's going to make it solid. And 0's a number. So put it. I mean, you could write 7.1 if you want, or 7.69. But 7.70 is a number. You know, and the problem is that students think 0 is nothing, and for some reason they think 7.7 is really precise. And actually it's not. Okay, it's less precise than 7.70. Okay, so make sure you write your zeros. Right, let's do another one here. Okay, now it hits right here. This one's going to be just hard. It's easy but hard. So, first thing, it's 8. Okay, but remember, it goes up by the tenths. So it's 0.1, 0.2, 0.3, 0.4, 0.5, 6, 7, 8, 9, 0.0. So so this is actually 8.0. It's not 8. Okay, so don't forget to write that down. All right, it's not 8. It's 8.0. It goes 7.9, 8. All right, this. Okay, right. You're not done. So you're sure that it's 8.0. You're absolutely sure. Okay, if you weren't sure about that 0, I mean, it's not 7.9. It's 8.0. I'm sure about that. Right. Well, how can I make this 0 solid? I just add another digit. And it could be any digit you want. You can write 0, 1, 2, 3, whatever. I'm going to put, in fact, I'm going to put another 0 because 0 is a number. So 8.00. All right. This 0 I'm unsure about, but this 0 right here I'm really sure about. Okay, now this it's easy but hard. Okay, so when you have a graduate scale or analog scale, there's a couple things to keep in mind. You are always allowed to write down one more digit than you can be sure of. So if the scale is in tenths, you can go to the hundreds. The other thing is zeros are numbers, especially at the end. Okay, so if it's 8.10, that's a real 0. Okay, zeros are real numbers. Don't forget those poor children, the children of the zeros. Okay. All right. Next thing we'll do is now that we got numbers, a lot of times when we collect our numbers, we have to do math with our numbers. And so is it going to see the same thing? Now that we have numbers, we'll often have to add, subtract, multiply, and divide. And we'll have to be careful about this because science math, just like science numbers, is different than math numbers. Or math to a certain degree. So let's do a simple addition problem with two scales from the scales that I did on previous. And let's say we weigh the two books, and I'm going to add their two. It's two books, two different books. So let's say scale A gives me a book that weighs 1.1 grams, and scale B has a book that weighs 1.1023 grams. Now you add these together, you go And the mass of these two books is 2.203. Okay, and your calculator, plug it in your calculator, and it gives you this. And you go, that's the answer, teacher. And you go, not sure. Because what does that number tell me? It tells me not only big it is, but how good my number is. And we have to be careful there, because how good is my number? Okay, the problem is that scale A only had a precision score of 2, and scale B has a score of 5. Okay, so when you plug it in your calculator, it just comes up with that number, but your calculator's dumb. It doesn't know the scoring. So right now, the answer has the score as the same as scale B, 2.0231, okay? It's a good scale. Well, should it have this score? Should it have a score of 5? Or should it have another score, or maybe an average of the two scores? Or should it have the score of the low one? Well, let's think about this, okay? And so in typically my class, I go through and explain this in terms of like a relay race. I mean, you could have, like in the say you have 4 by 100, and if you know what I'm talking about, it's like a track event, and you have the your first 3 runners are the fastest runners in the whole world, and then your last runner, so let's say they all run 100 meters in 8 seconds, okay, which is super fast, right? No, and then so the first guy, he gets 8 seconds, and he's like 15 meters ahead of the second place. The next guy's 30 meters ahead of, and so forth. And so they give the baton to the number 4 guy, and number 4 guy is really, really slow. He can only run 100 meters in 5 minutes. Well, who's going to win the race? Okay, it doesn't matter how fast your fastest runners are. You can only run you're only as good as your slowest runner. All right, you're only as good. There's this saying that says your chain is only as good as your weakest link. You can't give the score of your number. You can't give the score of your relay team to your fastest runners. Right? You have to give it to your slowest runner. Okay. So, and that's what's going to do here, is that we're only good as our slowest, our weakest link. And our weakest link is this A right here. So all we can do when we write down our number is we can't give it a score of 5, we have to give it a score of 2. We can't assume, and that's the thing, you just can't assume. It might be, it actually might be closer to 2.0203, whatever. But we can't assume that. And so what we're going to do is we're going to go, let's go on the, error, okay, the reason of error, all right? And so what we're going to do is give it a score of 2. And so the answer that we're going to write down is 2.2 with a score of 2. Now some students get upset and go, well, what happened to the other digits? Well, nothing happened to them. You just can't trust them, all right? And the reason you can't trust them is because of the slow guy, all right? So you're not losing numbers. We don't trust them. That's because of our scales. So let's come up with some rules of scoring, and then we'll talk more about this, adding and subtracting and so forth. So we're going to go basic rules of sig figs now, and we need to expand on these. One of the things that we're going to do now is that all of our numbers right now are going to have decimals. They will, even if you have to force a decimal on it, okay? So there won't be anything as like a 2. No, unless I tell you differently. All right, now sometimes especially when we do stoichiometry. I won't deal with decimals just because it gets things messy. But especially when we do labs, make sure you always have a decimal number. So like one of the problems, like students, they'll measure a temperature, and your on a thermometer, and the thermometer will be will go 20, 21, 22, 23, and then they'll see a number will hit 23. Okay, well, it'll hit the 20 and the 3, and then they'll just write 23. Well, remember, you're always allowed to write one more digit than you can actually um, see on your scale. So you need to write down 23.0 whatever. Okay, so always write at least one decimal. I mean, um, and what we're gonna do for now is, which is going to be a little different than what we just talked about, is that the precision score, or the number of sig figs, is going to be the number of decimal points. So in the previous example, we have 1.1, and then 1.1023. So actually, what we're going to do now is say this has a score of 1, and this has a score of 4. Okay. So actually, in the previous examples, and just know that. So what you're going to do is always count. The score is the number of digits right of the decimal score. Now the one thing that's going to be there's going to be a couple things. Is that sometimes you get a number like this, 0.000343452. And there's going to be different ways to account for these zeros here that are in front of these guys. Do we count them as real? I mean, do they count as our score? Well, sometimes they do and sometimes they do. So we call these leading zeros, where there's no other number in front of them. And we're going to see sometimes we count them as actually part of the score, sometimes we don't. So, like, if I just gave you this number here, and I ask you what's its score, what you do is you don't count these leading zeros. So the score of this number will be 1, 2, 3, 4, 5, 6. All right. So if you have decimal points and zeros, you don't count them. All right, and it gets a little confusing, but so we'll see how that works, and we'll go through it. For now, because we already used decimal, all zeros after non-zero numbers count. So these zeros count, but these don't. That's if you just look at a number. I mean, if I just put a number up on the board or on my PowerPoint, and I ask you what's the score, you would say that it has a score of 6. Now, we'll see if you go into 121, we'll talk about this, is that sometimes you have numbers that don't have decimal points, like 100, then you go, whoa, what do I do with these zeros? And right now, let's not worry about that. It gets the wrong interpretation, because you have to understand the context of what these zeros mean. So what we're going to do is we're going to talk about adding and subtracting, and multiplying and dividing. But one of the things you want to do is when adding, every number right of the digit is part of the score, which we'll go over. And the other thing is we'll go over that in a minute. And we're going to round. So the way that I round, like if you have a number like 3.35, I would round that up to 3.4. Okay, so that's the way I round it. And there's different rounding rules. Some people go every other digit gets rounded up and so forth. Okay, so now we're going to look at the two types of operations: multiplying, dividing, adding, and subtracting. So we're going to do multiplying and dividing first. So let's take these two numbers, 2.241. These are So I have a scale that measured this, and I have another scale that measured this. And I want to multiply two numbers together, and I kind of want to come up with an answer that tells me how big it is and how precise it is. So first thing you do, and there's different ways you can do it, but I'm going to tell you the way I do it right now, is just plug it in your calculator. And you come up with 7.6194. Okay, now this number just tells you how big it is. It doesn't tell you the precision. So what you need to do is you need to go back and look at both of the numbers' scores. You can see that this number here has a score of 3. This number has a score of 1. That means your answer is only going to have as many digits as your worst score, 1. So this is going to be 7.6. Okay? Okay, so now what we're going to do is adding, subtracting. So here's our two numbers, and these are actual, they're just not numbers, all right? They're actual numbers that you measured. Okay, so this scale give me this, and this scale give me this. I'm going to add two numbers together. All right, and treat them as just numbers. That's the first thing. Plug them in your calculator, and you get this number here. All right, now, then what you have to do is find the score for each one of these numbers. Now, for adding and subtracting, it's every number, every digit right of the decimal point. So this has a score of 1, 2, 3, 4, 5. Okay. And this scale has a score of 1, 2, 3, 4, 5, 6. Now your answer can only have the number score the same as your worst scale. So it can only have 5. And it's right at the decimal point. So it's 1, 2, 3, 4, 5. So your answer is going to be 2.20046. Now, the 1 hasn't gone away. We're just saying we can't trust it. Okay, so the difference between adding, subtracting, and multiplication, division is leading 0. Now, a couple other things I just want to go over before we close this up. This sort of introduction to numbers and science, and hopefully it'll give you an idea how to treat numbers. Let's say, often, like, here's the number. I'll have students measure. One value is 1, one value is 3. They'll plug in their calculator and they'll come up with this number here. And they'll go, it's 0.333 repeating. Okay. And that just really, really gets me angry. All right. All right. So they put a 0 over, it says it's 0.3. Okay, in math, that's true. In science, it's not. And the reason is because if you say 0.333 repeating, it's telling you to say, every single digit to infinity. All right. And you think it's so clear that it's the clearest day in the universe, and there's no clouds at all, and we can't have that. There's always clouds. So don't do this. Don't do the 0.33 repeating. You have to pay attention. So let's say you measured 3.0000 and 1.00. You plug it in your calculator, and sure enough, it gives you this, because your calculator is dumb. All right, your calculator just gives you a calculation. All right, but we know this is that we have to. This number can't be true. Well, could be depending on how good our numbers is. But our actual number we write down, only could be as good as our worst measurement. So this has a measurement of 4. 1, 2, 3, 4, and this has a score of 2. So my answer can only have a score of 2.33. Okay. And the other thing is that, don't use fractions. So I told you guys you could use fractions like in stoichiometry and things like that. And I'll let you know when you can do it. Don't use half. you're going to use 0.5 or 0.50 depending on on your on your uh, on your measuring device. And like I said, calculators are stupid. That's it's I mean, they're inanimate. They just do what they're told to do. Um, so when we put the above problem 1 divided by 1.00 divided by 3.00, it just writes down 0.33 repeating. It doesn't. It just gives you a number. It doesn't tell you how good that number is. So what you can do is use your calculator to get the number first, and then what you do is basically sculpt the number to get the right precision score. Okay, and that finishes up your introduction to numbers and how to use numbers. And so we don't want to make it too complicated right now. Right now is that you just got to understand the concept of numbers. Is that they have two properties. They tell you how big a number is, and then how good that number is. And you got to pay attention. You got to pay attention to zeros and yeah, that's a big thing. So that ends this number thing, number intro, and if you're taking 121, we'll expound on this.